in the HE Linen Engineered to Perform webinar series. My name is Deborah Golden, and I am the Inside Sales Representative at HE Linen, and will be your host today. Today's discussion is on regulator performance and the effects of lockup, droop, and choked flow. Our guest today is John Kestner, Product Manager on Valves and Regulators at Swagelok's headquarters in Solon, Ohio. John joined Swagelok in 2009 as a technical service representative and has also had roles as an inside technical sales engineer and field engineer. Now, before we get started, I have a few housekeeping notes for you. As it pertains to our dashboard, you will notice that there are several widgets at the bottom of your screen. The first is a speaker bio page where you can learn more about John. Also, a slide widget, and you will notice the On24 screen is not like other webinars. You have the ability to move the boxes on the screen by clicking and dragging them into areas that are comfortable for you. Next, there's a survey link, and I'll tell you more about that at the end of our presentation, but there will be a survey. Then we have a widget for Q&A, and as you listen to the presentation, think about what your regulator questions are. You can type them in at any time. After that, you will see a resources link, and here you will find an extensive library of regulator information that may be of value to you. And then finally, there are links to our LinkedIn page and our contact page. So today's webinar is also very interactive. We want you to ask questions and respond to our polls. Now I'm going to turn it over to John. John, welcome. And thanks so much for being with us today. We're looking forward to you helping us understand the role and function of.
Yeah, thanks for having me. And I want to say good morning, good afternoon, good evening, good middle of the night, wherever folks are around the world. My name is John Kestner, and I'm the product manager for pressure regulators for the Swagelok company. And I'd like to take some time today to talk through pressure regulators. And, you know, I want to first start with the theory of pressure regulators. So how do these things work? What are the basic types? What makes them tick? So that's really going to get into the balance of forces. And then spend the bulk of our time on regulator performance. So that's lockup, droop, choke flow, supply pressure effect, things that we see in a day-to-day usage of pressure regulators. And then we'll obviously come back and review at the tail end. So when we think about pressure regulators, there's really two types. There are pressure reducing regulators, which they do exactly like what they sound. They reduce a high pressure gas or liquid down to a low usable pressure that's safe for the process and for the operators. And then on the back end, there are back pressure regulators. So back pressure regulators really are used to put an upper limit on the upstream pressure. So a pressure reducing regulator will control what's in front of it. So it really cares about what it's looking downstream at as far as pressure, and a back pressure regulator cares about what's behind it. Now, in general, most folks, when they think about pressure regulators, they think about a pressure reducing regulator, and that's mainly what we're going to be talking about today. But I don't want to ignore back pressure regulators, so if you do have questions, use some of the interactive features that we have, and feel free to ask questions about back pressure regulators. But the majority of our time will be spent on pressure reducing regulators, as that's the bulk of what we see in the market. And so that'll bring us to the first poll question. And if you see the poll question, feel free to answer what percentage of pressure regulators in the field that we experience, or even that you have at your own sites, are pressure reducing versus back pressure. We should. So looks like a few of the results are coming in, and it's exactly where we see it in the field, in that about 3/4 of pressure regulators used out in the world are pressure reducing types. So many folks use gas cylinders or other high pressure sources, and those pressures must be regulated in order to do the work that we're asking that gas to do in a safe way that's not going to put our folks in a position where there's thousands of PSI on a lab bench where maybe you only need 60 PSI. So that's absolutely spot on, that most of the pressure regulators we see are the pressure reducing type. So what I want to do is talk a little bit about what makes those regulators work and how can we, as pressure regulator users, use the knowledge we have of how the underlying forces act in a regulator to make choices in our regulator selection, and also how we use them to maximize their efficiency in our system. So pressure regulators, and you'll see through this presentation I used a lot of cutaways of Swagelok products because that's what I have access to, and that's really what I talk about. But all of the concepts and the componentry and forces we're going to talk about apply across the industry. So don't think that many of these concepts are Swagelok specific, although we will use Swagelok product for a lot of our cutaways and demonstrations. So when we talk about pressure regulators, there's a lot of components that go into making a pressure regulator function. We really only care about 3 groups of pressure regulators that help us do what we want a regulator to do, which is take a high pressure gas or liquid and convert that into a low pressure gas or liquid at the flow demand that we require. So that's why folks use pressure regulators. That's why folks buy pressure regulators. They don't buy them because they're shiny and they have colorful handles. They buy them because they need low pressure gas or liquid. And there's 3 sets of components that help us do that. The first is the control element, and that's your collection of the poppet and the seat, or the valve and seat, and that's really where your pressure drop happens. So when you have a high pressure gas that comes into a pressure regulator, a certain amount of flow needs to get across the seat, and depending on how big that seat area, the flow area is, there will be a certain amount of pressure drop. So that valve in a pressure regulator will always be adjusting itself to give you, the user, the pressure drop, the low pressure that you would like. And that's the control element. So that really is what modulates and makes the regulator deliver that pressure drop. Now the next is the loading element. And this is really the only piece of a pressure regulator that we can control as regulator users is the loading element. So most often in a direct operated spring-loaded regulator, that will be a spring. There are other types of regulator technology that we won't get into in this webinar, but things like dome loading, electronic loading, pneumatic ratio loading, there are a fair amount of control schemes. For our purposes today, we'll talk all about direct operated spring-loaded regulators. So it's far and away the most common type, and we'll be spending most of our time on that. The way that we interact as a user with the loading element is through the control handle or the control knob. So that's your knob on top of the regulator. Sometimes it's even as simple as just an adjustment screw. But as we compress that spring, our loading force changes, or as we allow that spring to relax, the loading force will change. So really that's what we have control over. It's the only thing today that I'll talk about that a regulator user has control over with the regulator unit. Now the last and third component set that we care about ties the control element and loading element together, and that's the sensing mechanism. Most often it's a diaphragm or a piston, and its job is to look at what's happening downstream of the regulator. So in that low pressure zone, it takes that pressure, and pressure applied across an area will give you some force. And that force will translate against the loading element and balance with the control element in order to create what we call the balance of forces. And so that's what I want to talk about next. The way that these three component sets interact drives almost all regulator behavior in the field, and certainly is something that if you're troubleshooting or trying to understand the behavior of a regulator in a system, you can always come back to the balance of forces for some insight into what may be happening. And you'll hear me talk a lot about the balance of forces today as we go through some of the concepts. So the first force is the loading force. Now, I mentioned before, that's what we control. As a regulator user, I have control over that loading force. I can turn in the handle to increase the loading force, compress the spring, or I can dial out the handle, allow that spring to relax, and allow that loading force to lower. Next is the inlet spring force. So this is part of the control element. It is a light spring that's present on most every general industrial direct operated spring regulator. The purpose of an inlet spring force is to help keep the valve close to or closed on the seat if there's a low inlet pressure. So the way we get closing force, so if the regulator needs to shut off, is a combination of the inlet spring force and ultimately your inlet pressure, which we'll talk about. So the inlet spring force is low. It's not a large force, but it is there, and we need to consider it inside the balance of forces. Next, if F1 is what we control as regulator users, F3 is what we really care about. So you buy a regulator because you need low pressure gas or liquid on the outlet. And that's really what your F3 is. So the F3 is that outlet pressure acting over the sensing mechanism. So whatever area you have, whether it's a diaphragm or a piston, will create some force based on the pressure and the area. Finally, you have the inlet pressure force. So the inlet pressure force is exactly what it sounds like. It's the force generated by your high inlet pressure. And that is a function of the unbalanced area in the control element. So there's always some area for the inlet pressure to work on the valve to help close the regulator should there be no flow. So if you can imagine looking at the directions of these arrows, really the three on the bottom half of the regulator, F2, F3, and F4, work to balance against F1. And the regulator, any regulator will work to maintain or create this balance as system variables change. So if you have a flow demand increase, if you have an inlet pressure change, or a user comes up and changes the position of the handle and changes F1, the other forces will work to balance out. And most often that's a change in the position of the control element. But sometimes there can be some other reactions, and we'll talk through many of those today. So before we get on to some of the performance criteria, I'd like to pause for just a moment and check any of the questions that we may have. And looks like folks have answered them so far. But if you do have any questions on the balance of forces or any of the regulator types, feel free to shoot a question in, and we'll be sure to get it answered just as soon as we can. So moving on to pressure regulator performance. These are concepts in pressure regulator behavior that we see in day-to-day use. So as you're using a regulator, you will notice these phenomena throughout the day, depending on what you're doing with a particular system. The three main pressure regulator performance characteristics that we talk about are lockup, droop, and choke flow. And what we'll do is use a pressure regulator flow curve to describe these behaviors. We'll actually start at the far left side of this curve, work our way through the middle, and then finally end at the other side. Now I want to stop here for just a moment and talk about what a pressure regulator flow curve tells us. These are pieces of technical information that are most often available in pressure regulator catalogs or technical literature, and what this tells us is what to expect from a pressure regulator at a given inlet pressure and a particular outlet pressure set point as the flow changes. So your bottom axis, the x-axis there, is your flow. So as you move left to right or right to left between your flow ranges, you can follow the curve, the particular curve you're on, to get an idea of what to expect from that regulator as your system demands or parameters may change. We'll talk a lot more about these throughout the session, but I did want to talk about the importance of flow curves in selecting the correct regulator, in that regulators, as we just talked about, are very dynamic pieces of equipment. So it's always important to understand how they will react to differences in the system parameters, and as things change throughout the day or throughout a test or throughout a process run, it's always best to consult the regulator flow curves. So we'll start on the left side of a regulator flow curve, and this is in a zone that we call lockup. So lockup is the behavior of a regulator as it moves from a static to a dynamic state. And so what I mean by that is that if you have a particular test that's happening on a lab bench and there is no flow, and then you crack open a needle or metering valve to initiate the test, that's going from a static to a dynamic position for the regulator. And then similarly, done with the test, close up your valves and the flow will go back to zero, so slowly go back to zero, and eventually the regulator will shut off. So I'll take this moment to talk about regulators and shutoff, in that they're not shutoff devices. As we talked about in the balance of forces, we have a very limited amount of closing force. Really, it's the combination of the inlet spring force and the inlet pressure that gives you all of your closing force, but they will shut off. So it's always best to have a dedicated shutoff device in a system, but understand that the regulator will shut off and you will see some form of lockup. In every pressure regulator, there will be some form of lockup. And really what drives lockup is the compression and creation of a positive seal on the seat. So if you can imagine that same test happening on a lab bench, as the flow is shut off, so as the needle valve or metering valve is shut, or for that matter even a quarter turn ball valve, as that's shut off, the flow will decrease. As the flow gets almost to zero, that valve, in the control element, will be very close to, if not touching, the regulator seat. But in order to create that positive seal, there is an extra push that's needed. So until that seal is made, you will see a sharp pressure rise get past the seat. And that's really what you're seeing with lockup. Now on the other side of it, you need to give all that back. So when you start the flow again, you'll see a small tick down on a pressure gauge, and you'll see a quick drop in pressure, and that's really just giving that pressure back. So in order to create the seal, you need to use some of that force, and then you have to give it back on the back end. And again, it's a characteristic of most every pressure regulator. There are things you can do and choices you can make to minimize lockup. Softer seats are always good. A smaller seat, in fact, will have a smaller lockup, less forces involved. So there are choices that you can make if lockup is very important to the operation of your system. Next, I want to talk about Droop. So Droop is far and away the most commonly discussed aspect of regulator performance. And when we talk about Droop, it's the change in pressure as your flow demand changes. Most often, this is a reduction of outlet pressure as you increase your flow demand in the system. So you will notice as you look at flow curves and as you use pressure regulators, then you will see that there is a reduction of that outlet pressure as you step through a regulator's full operating range. What we want to understand is how does that droop affect the way that we use pressure regulators. So I want to ask the group, have you all heard, used, encountered the term droop prior to this session? Is this the first time that you've maybe heard the term but you've experienced it? I'd like to get some feedback on that as well. Yeah, okay, so that's a pretty typical 50-50 split that we see as far as folks encountering the word droop and maybe seeing it in industry. So what I want to do is talk through a bit of what does that mean for us. So why do we care about droop? It's something that, well, if I can set my regulator where I need to, do I really need to understand it? And I think it's an important concept because most often as we're working to either as regulator users or engineers specifying regulators, the problem is almost always presented as we need a pressure at this specific flow. If life were only that easy, then things would be a heck of a lot simpler. Most often what we see is that we need this pressure within a specific flow range. So what this means is that we need to understand what to expect from a pressure regulator as we move within that flow range. So what I'll do is I'll take a imaginary flow curve. So this is not for a regulator, any specific regulator, but it does illustrate the concept of how we utilize Droop in not only selecting regulators, but also how do you set them up and set the pressure of a regulator in the field. So if we take this regulator in a system that has a specific flow range that we're targeting. Regulator is installed, we're commissioning the system, and we set our desired pressure at the low end of the flow range. Now, this is great because we know we're going to get the pressure we need at the lowest end. What we need to understand as pressure regulator users is how does that affect the pressure as we move through the flow range. Now, you can imagine knowing that Droop is the reduction of outlet pressure as flow rate demand increases. When we're at the high end of this particular flow range, our pressure will be below the target. Now, this may not be a problem. It's certainly a safe situation. We won't have to worry about relief valves opening up, high pressure alarms going off, putting our folks in an unsafe situation, but it may also not be ideal for the process that we're working to accomplish. The test we want to do, the mixture we want to make, it may not meet the process parameters. So I like to think of myself as a clever guy, and I say, well, I know what to do. I can set it at the high end, and that also may be okay. So we know that we are at least going to have the desired pressure that we want at the maximum flow range. But what we need to understand, and knowing about Droop, we can think about this in looking at the flow curves, is that at the low end, so just like Droop is the reduction of outlet pressure as flow demand increases, the outlet pressure will increase as flow demand decreases. So at the low end, we will have a higher than desired outlet pressure. Now, again, this could be okay. Certainly it puts a floor on where our pressure will drop to. But if we have relief valves or the high pressure alarms, or we've got certain componentry downstream that can only handle a certain amount of pressure, we need to understand if that type of setting is acceptable and if the regulator can perform to a level that is required for that system. So finally, sometimes we don't always get the opportunity to set these regulators when they're in the field. Sometimes they need to be bench set on equipment that's calibrated and purpose-built for pressure setting and then put into the field once they're set, which is okay. There's nothing to say that that can't be successful, but it really puts the onus on us as users to understand that regulator's capabilities and how it will react to the increased flow demand. So as you can see here, if we set the regulator on a bench at our desired pressure with just a trickle flow, or for that matter even a static pressure, so no flow, we would be well below where our desired pressure is once we hit our target flow range. And this all has to do with understanding the droop performance of that particular regulator. Now, there are things you can do. So understanding flow curves, we know that if we only increase that bench set, so we lead the pressure a bit, knowing how much we expect that regulator to drop in pressure to get to and through the flow range, we can anticipate and set the regulator to give us good performance throughout that entire flow range. Now, we may also say that the low end is just a little bit too high and the high end is just a little bit too low, so what options do I have there? And really that's where comparing the flow curves of two different regulators can become very helpful, in that you may find a regulator that has a flow curve or performance that looks a lot more like this. So when folks talk about regulator accuracy, most often this is what they're talking about, in that if I have a certain flow range, how accurate will my regulator be, or how little droop will I have across that flow range? Now, as you can imagine, in order to get that added accuracy, most often you add regulator loading technologies. Sometimes you need to add a pilot, go to a dome-loaded solution, sometimes even electronic loading to get the most accurate solution, and those can all add complexity and cost, which is why it becomes that much more important to understand the capabilities of a particular regulator that's in a system or that's been specified to know if it will work for that particular process or application. So before we go on to the poll question, I'm going to send a pulse check to everyone to see if there are any questions, and let me know if we are hitting on the topics and that things are you all are picking up some of the concepts that we're talking through, and I'll leave that up until we go through the next poll question. So I want to ask the group, how are regulators typically set? At the site that you work at, the organization you're in, how are they typically set? And as those poll results are coming in, I'll go ahead and check any questions that you all may have. So the question is lockup the same as deadband? And it can be, and we see a lot of control valve type terminology that's used with pressure regulators, and it's most analogous to deadband, yes, in that you really can't get good control within that lockup, and if you have two regulators, especially a pressure reduction regulator and a back pressure regulator, you will need to set them some distance apart outside of that deadband so that you can get good control both on the pressure reducing and back pressure side of the control system. I'll look through. It looks like we've got a few more questions. Let me make sure I can get through these. So we did just get a question on is the droop curve determined by the regulator or its spring? That's an excellent question and something that we will talk about in the few slides ahead. And the answer is a little bit of both, mostly determined by its spring, more specifically the spring rate of that spring. So great question. We'll talk about it in the few slides coming up. Next question was, does a back pressure regulator help flatten the droop curve? Not necessarily. You can get a little creative and help bleed off some of the excess pressure. So the top end, the example we had where the pressure will increase as flow demand decreases, you could have a back pressure regulator that bleeds some of that off to flatten it in an artificial way, but nothing that will directly flatten the droop curve of a pressure regulator. Most often, in order to improve droop performance, increasing differential pressure can help. Having a regulator, as the last question just asked, with a lower spring rate, which we'll talk about, can help. And then also looking at different regulator technologies, so dome loading, pilot operated, external feedback, electronic loading, those can help to flatten the droop curve as well. And then finally, what causes the lockup pressure? So as the regulators will work to shut off, as the flow goes to zero, you will not get a full positive shutoff until the seat material has been deformed enough to create that seal, and until then you'll continue to see that pressure bleed by the seat. So until the inlet pressure and the inlet spring create enough force to do that, you'll continue to see the lockup pressure increase. And so that's why things like soft seats, which can shut off very quickly and without much force, can show much lower lockup pressures than something with a hard seat. And similarly, smaller diameter seats will have a lower lockup than the larger diameter seat. And then finally, before we move on, it looks like we just had one more question come in. It is, as an engineer and specifying a regulator, how would we best communicate to the installing contractor to set it at the right point? So we often get asked to factory set pressure regulators, which can be very difficult and is similar to the challenge of communicating how to set a regulator in the field. The two most important points are obviously what outlet set pressure do you need, what flow rate should that set pressure be set at, and then finally, what is your inlet pressure? And that's important due to supply pressure effect, which we'll get into towards the end of this session. Really, you need those three things. You can get more specific in talking about temperatures and media, but those can really all be accounted for by doing a little bit of math that will take the pressure up or down by a few percent, and things that certainly we can help talk through if needed, as you all are specifying and communicating out to the installers where to set those pressures. In general, if it's best to have a regulator set in the dynamic flow state where it will be used, so within that flow range, we recognize it's not always possible, but you should have at least 5% of your expected flow rate when setting a regulator. That helps to get you outside of that lockup zone and into a good working area for the pressure regulator. So from there, it's all about understanding the flow curve and where the pressure will end up once you're in the target flow area. So yeah, all great questions. And I think now we'll move on to a bit of the results, and then finally talk through what causes droop and how do we think about it. So these are pretty typical responses. Really great to see that a lot of folks are setting them at the low flows, at the system flow, and so that's great to see. And then obviously E, when you have point of use regulators, a lot of that is just understanding how much can I turn this regulator in to get what's the max flow that I can get reliably, and we'll talk about that in the choke flow segment. So thanks again for the feedback here. So I've got a few slides here that will go back and forth between, and I want everybody to watch what happens to the loading element and the control elements as we move across the bottom axis of that flow curve. So we're going to go from 2 SCFM to 4 to 6 to 8, and I want to have everyone watch what happens to the loading and control elements, and then we'll see what you all think as far as what affects the droop performance of the regulator. So as we increase in flow, you'll notice that, and it might be a bit difficult depending on transitions, but what you'll see is that as we go forward in flow, the control element moves down. As that control element moves down, you're actually giving room for the loading element to relax. So what you're allowing that loading element to do without any input from the user is relax a little bit, and that's all due to the fact that if you had we'll skip back up here to the first one where we're working at 2 SCFM. So if we're working at 2 SCFM and another line downstream gets clicked on, another paint gun comes online downstream, right? You've now doubled your flow demand to 4 SCFM. The regulator can only see that as the flow demand increasing. So you can imagine that it doesn't react immediately. All it sees is that there is a higher flow demand, and before the control element has a chance to move, there's a very high pressure drop across that smaller flow area on the seat. So what happens is the regulator says, oh no, I'm out of balance, I need to rebalance. And what happens is the control element will move away from the seat and allow for a larger flow area. And when that larger flow area is achieved, so the valve moves away, now that pressure drop that was way too high and shot the regulator out of balance is a lot lower. So same flow rate, larger flow area, lower pressure drop. And the regulator is happy, back in balance. But a consequence of that is that the spring has had a chance to relax. So as the valve moves away from the seat, the spring can relax. Now, a pressure regulator stroke, so the full stroke, is generally about 25% of the seat size. So if you have this one's much smaller, but if you have a 10 millimeter seat, the valve would only move 2.5 millimeters. But the loading springs we work with, very high spring rates, so even a millimeter of movement can translate into a large change in loading force. So as we continue down the flow curve, we'll see that spring continue to relax and relax as we ask for more flow through the system. So it's very much an iterative feedback loop there. And I like to bring that up because it gives us a chance to talk about the fact that direct operated spring-loaded regulators are the quickest to respond to changes in flow demand. That's really why they're used pretty widely throughout industry. They're able to react to quick changes and handle those. They will show more droop than something like a dome-loaded or electronically loaded solution, but they can react quickly to those changes. So I want to ask the group, we covered this, but I'm hoping everyone's listening. Otherwise, I'm doing a poor poor job as a teacher if folks aren't getting the questions this one right, because we just talked about it. But I do want to ask folks, what do you think happens when that spring relaxes? And clearly, it's that it relaxes and the force will decrease. Now, on the other end, as the flow slows down or the flow demand decreases, the exact opposite will happen. The valve will shut, and that spring will be forced to compress, raising your inlet pressure or your outlet pressure alongside it. And so we can come back to the balance of forces. We just saw what happens when more flow is needed. When more flow is needed, the valve moves away from the seat to allow that flow. That way the F1, the loading force, the loading spring can relax, loading force goes down, and ultimately our poppet spring force is not going to change, not by enough to be significant. The inlet pressure force for this discussion we'll assume is constant. So the only thing that can react is your outlet pressure force to give that regulator the balance that it wants. So in that way, this is the first of the concepts we can relate back to our balance of forces, and something that, especially as you're looking at maybe odd behavior in the field, is always a good thing to come on back to. So I'll ask folks to select which forces are affected. Again, we just went through this, but yeah, I'd love to hear the responses on this one as well. Yeah, exactly. So obviously the outlet pressure force is important, and we'll pause here for any questions that folks may have as more poll results are coming in. Feel free to write the team with questions, and we'll give everyone just a few minutes to populate some of the poll questions. Okay. Yeah, absolutely. So those are the two forces that we really see, is the outlet pressure force and the loading force. So I mentioned before that we're going to start at the left side of the flow curve, work through the middle, and finally end up on the right side. And that's really where we've arrived, is at the choked flow range. So the choked flow range is important because it illustrates the ultimate capacity of a given regulator for certain regulator parameters, or for certain system parameters. Generally, when the CV of a regulator is communicated inside regulator literature, this is what folks are talking about, is the ultimate capacity, the full open position of that valve, where you're getting all the flow you could ever expect at that given inlet pressure. And really the regulator isn't regulating out here. It's acting as a restricting orifice, so more like a static needle valve than an actual regulator. This is not a good position to operate a regulator. Now, when we talk about selection, always we want to think about the flow curves and what that tells us about a particular regulator, and we want to use CVs as a tool to compare different sizes of regulators. So as a regulator with a published CV of 1.5 versus a published CV of 0.6 will have different flow capacities, but ultimately we need to consult flow curves to understand the performance of that particular regulator. Now, where CV is particularly useful for pressure regulators is determining the fail-open flow. So if there's a system where a relief device downstream of a pressure regulator must be sized, the CV can most often, the Swage-Lock CV certainly, and most often in industry, CVs can be used in order to determine what that fail-open flow rate will be. So I don't want to say that CVs aren't useful, because they are, but really the flow curve should be used to size the regulator for a system, because that gives you all of the information, both the flow capacity as well as what to expect. So finally, we want to tie these concepts together in that we talked about lockup on the left side, so that's really where the regulator is closing, and you won't get very good control, very repeatable control if you operate in that lockup region. Then we talked about droop through the middle portion, and finally choked flow, again, not a region you want to operate in, and it leaves us with the optimal flow range. So the first question I always get is, okay, John, what percent of the curve should I target? And the answer is really it depends on the regulator configuration and the type. It can be anywhere from 10% in from the left and 10% in from the right, to something even more narrow, 20%, 20%, or 30 and 30. And it has to do with the regulator configuration and the system parameters. So it's the best rule of thumb is to target the flattest, most predictable portion of the flow curve. And that's really what we want to know with flow curves, is what should we expect from this piece of equipment should something change in my system, and that's how we really define that optimal flow range. So before we get into supply pressure effect, which will be the last topic for today, I do want to check on some of the questions and pause for any questions that you may have. So one question that came in, what is CV? So that's it's a coefficient that describes the flow capacity of many different fluid system components, mainly valves. We talk about CV. It's a dimensionless coefficient that's based on the really the amount of water that can pass through a given piece of equipment at a 1 psi pressure drop. So it's a helpful way to compare different needle valves, ball valves, pressure regulators, gate valves. Really, most any pressure or fluid device will have or can have some CV, and it's just a good benchmark for how much flow can I get through a particular device. So yeah, great question. All right, so I do want to spend some time on the supply pressure effect. The supply pressure effect is the other side of the system influencing regulator behavior. So just like changes in flow demand can upset the balance of a regulator and cause it to react in a certain way, so can changes in the inlet pressure. So when we think about what could cause that, the most common by far is depletion of bottle pressure. So many folks run regulators straight off of gas bottles, and as you use that gas, the gas bottle pressure will deplete, and that will cause the regulator to react. And we need to, as regulator users, understand what that reaction means for us and how we can best plan for it or adjust for it. And again, I'll go back to the balance of forces with supply pressure effect. We've got our 4 balance of forces. And if we think about F1 and F2 in this situation are constant. For our purposes, those are constant. The only thing that we are changing is the inlet pressure. So in this case, let's imagine a bottle draining. So as that bottle drains, the inlet pressure will drop and our F4 will decrease. Now, as we saw with the Droop example, as F4 decreases, the only other thing that can maintain that balance, because they are on the same side of that equation, is F3. So F3 can react and it will increase. And so that's really where we see this opposite but equal supply pressure effect. I've heard folks call it the dependency effect, or even had one attendee call it the depleting cylinder syndrome, which I thought was
which I thought was particularly fitting because that's generally where we see it. So I do want to pose a question to the group. What forces are affected when the supply pressure changes? And I'll give folks a minute to respond to that while we take a look at any of the questions. Yeah, so one of the questions that we've gotten as you all are filling out the polling answers is, how do you compensate for viscosity when looking at flow curves? So if you have a liquid flow curve, most often those are done with water or water-like materials. And what we've found is that until you get about 10 times the viscosity, there's not a significant change in the behavior. Now, a good rule of thumb is if you are going up in viscosity, it doesn't hurt you to step up a size in pressure regulator or seat size within that range of pressure regulators. But beyond about 10 times, it becomes a pretty difficult exercise to accurately compensate with the flow curve, and that's really where it makes sense to bring folks in. You know, we're always willing to help talk through what regulator may make sense to use given a certain media. So, you know, about that 10 times is the limit for any significant change. Beyond that, it requires a little bit deeper look. And then the next one is, how often should you service or rebuild the regulators? Like so many things in pressure regulators, the answer is it depends. It depends largely on the system being used, where the regulators are being used. The particulate load certainly is important. Chemical compatibility. What we generally see is that for clean, dry nitrogen systems, really as vanilla as you can get, you know, an inspection every 6 months to a year, where you inspect the cleanliness of the seat, the integrity of the diaphragm, and then for any other corrosion is usually adequate. You can most often clean off seats with an alcohol swab, whatever it is, whatever's compatible, and keep the regulators in good working order. And then beyond that, if you have a high particulate load, the first thing to pay attention to is the seat. So most often you'll see particulate either build up or embed themselves on the seat, and that can cause shutoff problems leading to pressure creep. So we didn't talk about it in this session, but you can get creep across the seat if you have a seat that's been damaged or is dirty with particulates. So those are really the things to look at for rebuilding. Yeah, so thanks for the polling answers, and yeah, certainly the outlet pressure and inlet pressure are significantly affected when you're talking about supply pressure effect. So I do want to run through an example before we wrap up today on how this supply pressure effect may look in the field. Again, going back to a gas bottle, let's say this is filled to 3,600 psi. We have a single stage regulator, direct operated, spring loaded, that's set at 50 psi. Now, as our upstream pressure decreases, so that's the cylinder depleting by 1,000 psi, we would expect to see some change on the outlet pressure. Now, what we know is that we need to understand how much to expect. Most often, SPE is communicated in pressure regulator literature as either a percentage or a ratio. Swagelok uses percentages, and a good general rule of thumb is GI regulators, quarter-inch size, 1% SPE is pretty common, and it'll vary from there. But if we take this configuration as having a 1% SPE, what that means is for every 1,000 psi or every 100 psi that the inlet pressure changes, the outlet pressure will change 1 psi. So you get 1% effect on the outlet pressure of whatever's changed on the inlet side. So in this case, we see an increase of 10 psi. So the first thing is, what can I do to combat that? And most often, folks will utilize two-stage regulators or two-stage regulator systems. And we'll go through quickly how that affects the ultimate output of SPE. One thing I do want to make clear is that you won't be able to get away from SPE. It is the physics of rebalancing the regulator is what causes that, but you can make choices that will minimize the effect of SPE. Two-stage regulators is a very, very common way to minimize the ultimate effect of SPE. So if we take the same system and we say that our cylinder now has depleted 2,000 psi, so on the far left side you have your bottle, started at 3,600, now it's at 1,600. The first stage regulator set to 500 psi. Now that regulator, we do see the 1% increase. So that first stage acts just like the regulator we just saw, and that sees an increase of 20 psi. Now the second regulator, it has no idea that it's even connected to a gas cylinder. All it sees is, hey, wait a second, my inlet pressure has gone up by 20 psi. So that unbalances the regulator, but only slightly, and you actually see a decrease on the outlet side of 0.2 psi. So unless you're using a digital gauge, most folks, that's a non-change. And it really helps to minimize the ultimate output to the system when you have a supply pressure effect that you know is going to happen. And the reason for that is that you get 1% of every change. So the 20 psi, you only get 1% of that on the second stage, and ultimately you end up with a very, very small change. So in practice, you can see some of these regulators I mentioned are built as two-stage regulators. So as users, we only need to input an inlet pressure, take out our outlet pressure like we would any other regulator. For larger process-like applications, these are most often built of two discrete regulators. Very often the first stage is a direct operated, spring-loaded, rugged, really robust regulator to take the brunt of the pressure drop. And then the second regulator is your fine-tuned instrument that will have a very flat flow curve and good outlet pressure sensitivity at the lower pressures that you'll have on a two-stage system. So there's really two ways to go about it. Most often it's just split by size. A two-stage regulator in that 1-inch size would be massive and impractical. So generally you see those built as two systems. So before we get to the review, I want to be sure that I answer any questions that you may have. So one of them is are two-stage arrangements also recommended for cases of regulator failure? And they can be. So you can have two-stage regulator arrangements, sometimes called working monitor regulators, where actually there's not an SPE consideration, but you allow one of those regulators to take over the workload should the upstream regulator fail, let's say. So if it fails wide open, the second regulator can take over the load and allow the system to keep working should there be a need to continue operation while maintenance is done, or you can divert to a bypass, whatever it is, it's there to catch the load. So yeah, absolutely it can be used in that way as well. So one of the other questions, let me bring this up, is are there any concerns with placing a valve downstream? What if I want to change the pressure with the valve closed? So this is a pretty common arrangement in lab setups where you've got a point-of-use valve that you're turning on and off. If you need to change the pressure with a downstream valve turned off, there will need to be some way to vent that intermediate pressure, either with a self-venting regulator, so it's a feature of the regulator that allows it to vent off once the handle has been backed off a significant amount, or you can use a dedicated vent valve. Either one of those will allow you to change the setting on the regulator. And then finally, what is the most common failure of a regulator? The most common failure that we see out in the field is contamination of the seat. So we talked about it before, in that if there are particulates that build up on the seat, or sometimes we'll see a piece of tube burring that wasn't blown out all the way, that can find its way to the seat and embed itself there, it won't allow the regulator to fully lock up. And so that's the most common. Second is diaphragm cracks or fatigue failures over a long period of time. You'll see those. Those are really the two most common ones. Aside from the traditional chemical compatibility and things like that you'll see, those are really the two most common modes of failure specific to regulators. Yeah, good questions. So as we wrap up, I do want to review just a bit. We talked about two types of pressure regulators, pressure reducing and back pressure. The control, loading, and sensing elements dictate regulator behavior. So there are a lot of components that go into a regulator. Those three are the ones that really drive the bus on regulator behavior. And the balance of forces are what describes the regulator performance. So as you're looking at a regulator, you can almost always draw something back to the balance of forces. Droop is the reduction of outlet pressure as your flow demand increases, or conversely, it's the increase of outlet pressure as flow demand decreases. Your regulators are always going to perform best in the optimal flow range. You need to use flow curves to know what to expect from a regulator. And then finally, a change in inlet pressure will affect your outlet pressure, and that's SPE as we discussed. So with that, I want to thank everybody for joining us today. I'll stay on the line here for a bit if there are any other questions. I think Deborah mentioned the survey questions that you all have. Be eternally thankful for any input that you all have. Again, I really appreciate everyone joining us today, and like I said, I'll remain on the line if there are any other questions. Feel free to let us know, and have a good rest of the day.
Thank you so much, John, and just want to give a big thank you to John for his in-depth and informative presentation, and also thank our audience for being with us today. As John said, please make sure to take our survey. We really need your input here. Also, if you have any additional questions, you can feel free to email us at the email links noted on the screen. This entire presentation will also be available on demand later today, and you'll be emailed a link to save or share with your teams. Our next Engineer to Perform webinar will be in May, when we will continue to bring you subject matter experts on fluid system components. So thank you, and have a great rest of the day. Whoops, we have just a couple more questions, John.
Yeah, so I saw a few questions come in. One of them is, does regulator type depend on the type of compressed gas? It certainly can change the options you may choose inside of a regulator. From the very basic pressure reducing versus back pressure, it doesn't. But when you have different types of compressed gases, certainly chemical compatibility comes into play. And then you can also have considerations with things like hydrogen, whether that can permeate through some of the seals, and if that's okay or not. Maybe if it's not, you want to stay away from elastomeric diaphragms, go towards all metal. Things like oxygen certainly need to be considered with pressure regulators, and make sure that the regulator chosen for things like oxygen has either undergone reviews for oxygen service, or ideally been tested to something like ASTM G175 phase 1 and 2. That's a medical regulator test for oxygen. So certainly you want to make sure that things like that are considered. But in terms of the overall type, even within regulator technology, so direct operated, dome loaded, electronic, that's independent of the compressed gas type. Now, Where you can see some differences is if you have a regulator that's built with an assembled connector like a CGA that's specific to a gas, that can change. But again, it's more the options than the actual regulator type. Yeah, good question.
Okay, it looks like that's all the questions that we have today. Thank you so much, John. And just a reminder to everyone that the entire presentation will be available later on demand today. So thank you and have a great day.